Hi, my name is Kenny Raines. I'm a sales and manufacturing engineer here at LaCroix Precision Optics. Got Justin Trace with me, who's our advanced processing engineer. Justin just wrote a paper on 2D and 3D metrology, the importance of 3D metrology. So Justin, you want to talk a little bit about what the industry standards are right now for measuring Aspheres?
Sure. Traditionally, the standard has been a two-dimensional metrology using usually a profilometer that drags a stylus across the part through the apex.
Right.
And that gives the operator an idea of what the part looks like in 2 dimensions.
Okay. So you've got a 3D part, you're taking a 2D trace across, so you're seeing a sliver of the part. What's the pitfalls of a profilometer trace?
There's a couple of pitfalls. The first is potentially damaging the part due to handling it.
Right.
You know, just like cleaning, anytime you drag something across it, there's always a chance you're going to damage the surface, which once you've gotten to your final metrology, you really don't want to risk damaging that part after all that work's been put into it. The other danger is you only see really what's in that one slice. You don't know what's going on in any other direction. So there could be a lot of asymmetry in the part and you might not ever know it.
Right. So yeah, if you're only taking that one trace, you aren't seeing the entire part. Mm-hmm. So one way that's typically addressed would be taking 2 traces, one at 0, one at 90. Mm-hmm. You could take 3 traces, one at 0, 60, and 120. Which gives you an idea 3-dimensionally if you can see any asymmetry in the part.
Right.
But at the same time, you're doing whenever you combine all those profilometer traces, you're making a rotationally symmetric image of the lens. So what happens then at that point?
Yeah, you do that and you create this kind of false image of the lens, which reasonably represents the asymmetry that's in there, but not all that accurately. Really, it more tells you that there is asymmetry,
right,
and gives you some very coarse data to try to correct. Mm-hmm. But because that map isn't a true representation of the surface, you could actually induce further errors as well.
Sure. So the big thing is, with using multiple traces, you can see the asymmetry, but you can't fix it.
Exactly.
So that's where the 3D metrology comes in, and that's really what the paper is about. Yeah. Takes a case study with a 6-inch Asphere and goes over the big, drastic corrections that we made in 3D. But tell us, what does 3D metrology really offer us? What does that really get us as compared to the profilometer?
Yeah, so lately in general, 3D metrology has become more popular in Asphere manufacturing because it can tell you so much more. Just like an interferometer, it can tell you what every part of that lens looks like. And so that allows you to do more advanced analysis on the part, such as looking at Zernike terms, doing different spatial filters. It also allows you to see non-rotationally symmetric errors that you couldn't see with the line trace. Right. Such as spokes or coma, things along those lines.
Right, so with the 3D metrology, we're now able to feed that data back and see in 3D and do 3-dimensional corrections with our Satislow SPS 200, on our Optro machines, or even be able to feed those into our MRF machines, which Jesse, you worked at QED for 14 years, so we've got an expert here. Mm-hmm. To be able to work with those things. So we've got a lot of different tools in the toolbox. How do those tools allow us to go after tighter slope errors and things of that nature?
Yeah, with the wide range of tools we have, we can pick and choose them based on the errors we're seeing on the part, whether it's on a 2-dimensional or 3-dimensional measurement. And we can decide, okay, this type of error we're seeing, we need to smooth out these mid-spatial frequencies, say using a pad polishing technique. Or we have some rings that MRF would do really well at fixing. And we can leverage our strengths of those different tools as needed.
Each technique having its strengths and weaknesses.
Exactly.
And each one is somewhat complementary to the other one.
Yeah, there's no one tool that will do it all. So we have a variety, so we can pick what's best for the given situation. And any given Asphere might see 3 different polishing tools to touch it based on, and some might just see one. It really depends on the needs of the customer and the geometry of the part.
Right. Good. I think the other thing that really we've been pushed on is slope errors in general. It seems that over the last 2-3 years, slope errors have really it's become more demanding, trying to make a smooth Asphere. And we've come a long way, especially really in the last year to 2 years. Mm-hmm. What do you think are really the big drivers of helping us be able to produce smoother parts with lower slope errors and also address mid-spatial frequencies?
Again, I think it's our range of tools. If we're having slope issues on the part, we can better address them because of what we have available. And I think a lot of what's driving it is lens designers are more savvy now. They understand that we use sub-aperture tools for doing Aspheres, and it could generate these things. So they're more likely to specify, hey, we need a good slope on this part. And if we know that, we can, the way we process it will change accordingly to make sure they get the part they need.
Right. You know, in your paper, you talk about, we did that case study on the 6-inch Asphere where we took a profilometer trace. I believe it was about 3.5 microns of form error in 3D, but in 2D, it actually passes spec.
Exactly.
And so the 3D image allowed us to see some asymmetry that we had just so happened to pull a trace across the best part of the part on accident.
Yeah, and the part was had mostly astigmatism in it, which if you do two 90-degree traces and you optimize each one to the best fit radius on that trace, it'll actually look symmetric. So if the metrologist doesn't notice that, okay, the best fit radius is a little different on those two, they'll think, hey, this part is good. 90 degrees, 0 degrees, we get the same answer. It's good.
Right.
But the 3D metrology, there's no interpretation needed. It's obvious looking at it. The number tells you this is bad. So you don't need that interpretive ability.
Yeah, and that was really eye-opening to me whenever we were making that part and being able to see the difference between the 2D and the 3D metrology. That's all in the white paper. So I guess my last question would be is, why would somebody choose LaCroix Precision Optics as an Asphere manufacturer?
I would choose us because we have a lot of tools here that we can use to address whatever the situation is. We're not limited to just using one manufacturer's tools. We're not specialized that way, so we can pick and choose based on what's needed for that part. And as things come up, if we have an unexpected result and we need something to fix it, hey, we'll just change machines and we'll address that situation. And we do everything in-house. The blanks come in here, and we do everything else in-house. We don't have to send it anywhere else to be coated or have the spherical side done or generate the Asphere for us. We do it all here, right in the U.S.
Yeah, that is a significant advantage. Well, everybody, be sure to check out Justin's white paper. Justin, appreciate your time today.
My pleasure,
Thank you.